Okay.
All right, here we go. Okay, so today we'll talk a little bit about simplicial homology. Which brings together the two threads that we've talked about thus far. We've talked a lot about homology, chain complexes. And that's been the majority of what we've talked about. And the other thing we've been talking about very recently is abstract simplicial complexes. And if you put them together, this gives you simplicial homology. Okay, now, this is algebra. This is, well, this is combinatorial topology. When you put them together, this is what is generally called algebraic topology. So at a high level, what we're going to do is we're going to take an abstract simplicial complex and what we're going to do is we're going to turn it into a chain complex. And then that chain complex, well, then we know what to do with it. We compute its homology. And the idea is, if we do the squiggly arrows right, then this algebraic object should in some way reflect properties of the topological object. The idea is algebraic properties and topological properties should somehow be related to one another. And the goal of algebraic topology as a discipline is to understand this correspondence. Now, it's worth noting that there are various other things that you could put on this side of things, on the topology side. You could put CW complexes. You could put things called cell complexes, or just general topological spaces. And in those contexts, the recipe is still much the same from a high level. The recipe is take your topological space, turn it into a chain complex, and then analyze the homology of that chain complex in the hope that that homology tells you something about the topological space you start.
X represents a topological.
And X then, in that case, represents a topological space, not just an abstract simplicial complex. But what I'm going to show you today is for abstract simplicial complexes. According to the schedule, I was going to talk about CW complexes and geometric realizations. In some sense, I got bored and I wanted to do this first because this is cool. So it is. Okay, now, before we go into detail on constructing these chain complexes, we're in the midst of, most of you, I hope, writing code for the first project. And we've been discussing about computing the homology of things, of chain complexes. And so one of the things that's cropped up is there's a variety of ways you can access this homology. You can compute it the way that we've done in class, which is build a basis for the kernel, examine basis element by basis element whether or not they're in the image of the previous matrix. That's perfectly fine. You can write that in code, enshrine that in Python, and all is well. Yeah?
Is that technically going from homology of chain complexes to linear algebra?
Yes.
Okay. That's what you're-
Well, in fact, it's going chain complexes to linear algebra. In fact, that's happening here.
So
You're-
we're
you're-
always
you're-
going to use that one.
Yes, you're asking a representation question. All right, I will, for the benefit of the category theoretically inclined, such as yourself, you've made that very clear. You have some category of topological spaces. You turn it into a category of chain complexes, and finally turn it into a category of vector spaces. And these arrows are in fact functors. And so from a representation theory standpoint, this is the representation process. So we're finding a way to come up with representations of topological spaces. Absolutely. Okay, cool. So what I wanted to do is, before we delve into the mechanics of computing, of building the chain complex for abstract simplicial complex, I wanted to circle back and look at computationally at how we compute homology. And there's a variety of different ways. There's a way I mentioned in class we've done. There's another way that I've alluded to, especially in the project description, about using projections. And I wanted to elucidate that because it's actually rather elegant and, well, if you do it right, it can be rather short in terms of the code and reasonably efficient. But perhaps a little more opaque. Actually, I will admit, completely more opaque. We were just looking at this in my office a little while ago. And I spent some time staring at these 2 lines of code, being rather mystified, even though I myself had written them about a month and a half ago. Now I understand what they are, and I want to show you what's going on under the hood, so that you can also be helped.
Now that you understand them, are you going to comment?
I'm not really sure. That's a really good question.
You should do that.
Well, it's 2 lines of code, and there's so little code there. That's an ethical dilemma for another day. Yes, generally I tend to be rather militant about commenting, but this, I don't know. I'm not sure. The comment would have to be a picture, and you'll see the picture. Okay, so here's how this works. So this is using projections. This is some of the side for project 1, and I will comment that this is optional.
Project 1 is optional?
No. No, I'm giving you an optional viewpoint on project 1. Okay, so we're going to use projections to compute homology. Okay, so the starting point is I have a chain complex. And I'll excise a bit of my chain complex here. Got the chain complex, and I want to compute the homology at CK. Now, I don't want to represent this as the official quotient space, or all the cosets floating around, because my computer's not going to be happy about being asked to carry around an infinite set. So what I'm going to do is I'm going to represent the homology as a basis for a subspace of this topology, of this vector space rather. So basis for the subspace of this vector space, which is in the kernel and out in the kernel of this guy and outside the co-kernel of this matrix. Now, the way to do this, you can do this in a variety of ways. What we've done in class thus far is we come up with a basis for the kernel, and then we merely, for each basis element, ask, is that in the image of this matrix, 1 by 1? And that's totally fine. That's perfectly passable. There's a nice loop that does that you can write to make it happen. On the other hand, this other way is kind of neat. So the idea is, what I'm going to do is I'm going to say, well, this kernel of this matrix, well, what is it? It's a subspace here. Now, it's a subspace specified by a bunch of columns. 1 column for each basis element of the kernel of this matrix. It's 1 column taken from here. Now, one way to think about that, instead of thinking about it as a subspace like that, if you think of it as a matrix, and in fact, I gave you a piece of code that computes the kernel of dk. And what it does is it returns a matrix with as many rows as dimension of ck, and as many columns as dimension of the kernel. Well, matrix is linear map. So this is a linear map taking you from K, which has got the dimension of the kernel, into my space. And this is the output of the function, kernel dk. So if you call this piece of code kernel dk, what this is doing is this produces a matrix whose output is in here and whose input is in this abstract space of kernel elements. Well, that's kind of interesting. So it basically took this matrix here and produced this matrix. Now, we know this is a chain complex. Because this is a chain complex, there's something very special. Well, what do I know about the image of this map? Where does it lie? Inside the kernel. All right, so it's inside the kernel here, but this also is a copy of the kernel. It's been sort of abstractly pulled out. So, because this is a chain complex, there's actually a map over here. Call this map M. So, M exists because we have a chain complex. Now, it's kind of, how do I find M? Yeah.
Sorry. So we know that the image lies inside the kernel because all adjacent compositions of two matrices have to go to the zero matrix?
Yes, precisely. Precisely. Yeah.
So the output of the kernel, you said, is a matrix, right?
Yes.
So if the output of a kernel is a matrix, why is it that the arrow is pointing to a vector space?
So the matrices are actually the arrows between the vector spaces. They're linear transformations.
Oh, so the output of the kernel thing is
Yes.
actually the arrow?
Is this arrow, this matrix.
Okay.
It is this arrow, this matrix.
And the input is yet
Is-
another arrow?
The input here.
Is, the input to that kernel function as a function. The argument is,
okay. Okay, so this function, what it does, is it takes an arrow, yes, and produces another arrow. You're correct.
very nice.
Yes.
I like that.
Yeah, there's a nice category theoretic interpretation of this, as you can imagine. We're not going there.
Yes.
We're not going there. Okay, so, but this M exists because I have a chain complex. The image of this guy has got to be in the kernel of this guy. Now, what's sort of implicit in saying this, though, is that, well, this diagram should commute. Which is to say, so that, what has to happen? Well, dk plus 1 has got to be, first do M, then do this kernel matrix. Right, this composition, remember, this is composition of functions. It's also matrix multiplication. So what we want to do, if we want to find M, is we want to, like, move this over to the other side. Well, how do I move this over to the other side? This is just some matrix. Matrices aren't typically invertible, especially if they're not square. This matrix is probably not square. If it's square, you have a hope of inverting it. It doesn't necessarily have an inverse. But sometimes matrices have left or right inverses. They're not full inverses, they're not two-sided inverses in the sense of usual matrix inversion. But sometimes you can still push this thing over to the other side by doing some linear algebra. This is solving a system of linear equations. So roughly speaking, what we want to do is we want to take this guy and put it over here. And this is done using our friend np.linalg.lst, least squares solve. Basically solves this system of equations. It's a little bit backwards from what you're used to, because usually you want to solve ax equals b. Well, here's a, here's x, and here's b. So it's kind of backwards a little bit, but no matter really. So in fact, you can do something like this. You can do something that looks like something like this. And that will return your matrix M.
That's your homology.
No, we're not there yet.
Right.
This is purely computing this map M, which is basically mapping this space into the kernel. So remember, the image of DK is a subset of the kernel. Well, what I've done is I've taken the kernel, I've pulled it out on its own. But I know the image had to be in the kernel, so I'm just purely moving the image of this map into this kernel. But now is where we do this is where we do the important part. I also give you a function, co-kernel. Co-kernel tells you, instead of all the vectors that get sent to 0, all the vectors that never get sent to. They're the ones that are outside the image. Well, what am I looking for in the homology? Looking for all the vectors that are in the kernel but outside the image. Oh, well, that should be like a subset of this thing, or a subspace of this one. Well, how do I make subspaces? I made subspaces by pulling out an arrow. Oops, misdirected my arrow here. My homology is then purely just the co-kernel of, well, what am I looking for being outside the image of? Being outside the image of M. That's my homology space. So take a look at this M, compute its co-kernel, and that'll tell you the homology. Now, what are the rows and columns of this? Well, the columns of this, then, are in fact the generators of homology. Each column is a homology generator, so this has got as many columns as dimension the homology will have. Because remember, it's capped off by the size of the kernel. Everything in here is definitely in the kernel, and everything in here is definitely outside the image of M, which was the image of D, just rethought of as over here. Now, this is not what we want the output of our homology pairwise function to be. We want that to be, the columns are individually elements of this space. One column for each generator of homology. Oh, but that's not so hard, because how do I get there? Well, I start out over here, this is what I've now computed. I want to think of them as being in here. Well, how do I get there?
Co-kernel.
Yeah.
Kernel composed of co-kernel.
Literally just compose these two matrices. So the output of the homology pairwise function is purely compose those two matrices, i.e. matrix multiply. And what this does then is this instantiates your homology as being a subspace here. Now, it's not canonical in the sense that I could have chosen various other bases and still gotten an isomorphic space. What you really determined in computing homology is the number of columns. That makes this a lot easier. So this is a little bit more sophisticated way to look at the computation of homology, sort of diagrammatically, and making use of the fact that you've got some linear algebra already built in. Now, if you're purely doing the more pedestrian way, like what we've done in class, computing the kernel and asking, is this basis element in the kernel in the image here, we're still using the same function. But we're using it one at a time rather than all at once. The all at once, this is compiled Fortran. It's about as fast as you will ever get on a computer without actually, no, just about as fast as you'll ever get. So if you do it all at once, you save a lot of computation. Yeah.
Still hung up on the kernel function.
This guy.
So that kernel function, it's going to send, the output of that function is a function. And it's going to send something from the kernel K to the second space in the chain complex CK.
All right, look, this has a special name. This is called an endo function. It takes a collection of spaces and maps, picks them up, and dumps them right back on the same thing. Same set of spaces and maps, but they've been rearranged a bit. So in particular, what it's doing is it's basically grabbing arrows and moving them around in the diagram. So I'm taking this matrix representation of this map, and I'm computing, well, I want to compute the kernel of that matrix. The kernel of that matrix is not a matrix. The kernel of this matrix is a subspace of the domain.
Right.
Subspace of the domain means that it has a basis.
What are the columns of that matrix?
And those are the columns of the matrix that the thing returns. But now what we've done is we've just said, okay, well, if I want to then, say for instance, specify a vector in the kernel, what do? I take the basis and I put some coefficients in front of it.
Okay, so is this space K, is that just like, say, R3 or something?
Yes,
Okay.
yes. I'm leaving it abstract because I never actually really need to ask for it.
Okay.
Because really, when you're doing computational linear algebra, you're always working on the level of matrices, which are the arrows. I never really have to fill in what the spaces are.
Okay.
That answer your question?
Yes.
Other questions?
Kernel is a set of vectors, correct?
Yes.
But in the output, it's a matrix.
Yes.
So you only have to reference it, you don't have to reference like each.
That's right.
You only have to reference the kernel. And
Yeah.
pull that out.
Now, you can, if you wish, pull out individual columns through slicing.
Yeah. But,
Well, if you're using this approach, you don't need to. If you're using the approach of taking each individual vector and asking, did it come from here? Then yes, then you need to slice them apart, and that's fine. It's a totally reasonable approach, and it works just fine. Whatever happens to be easier to understand and easier to write, go with it, and correct. Okay?
Size of code like this or size of code like this?
Well, yeah, but, all right, look, I will say this. Size of code like this that makes a lot more sense versus size of code like this that is not as easy to understand, there's also that balance.
It's cheap to store a couple strings, but it's expensive to teach programmers more advanced math, so.
Yes, well, even I'm saying now, I spent a good 20 minutes looking over my 2 lines of code that implements this before I was like, oh, this is what it's doing. And I had to draw this big diagram. I'm quite sure I did not draw this diagram when I wrote the code. I'll just say that right out. Now, I was reading a lot of category theory, so maybe it was stuck in my brain, but I did not draw this diagram until half an hour ago when I first drew this diagram with Danielle. Okay. All right. So now let's talk simplicial homology. This is computational. Now let's do a little theory, but link it to the computation. And simplicial homology starts out with a really simple idea. The really simple idea is if I've got an abstract simplicial complex, I know what its dimension is, and I know what faces are subfaces. The simplicial homology the idea for an abstract simplicial complex X, if we know one simplex, say delta, okay, we can easily access all its subfaces. And the easily part of this is important from a computational standpoint is recursive. recursively access all of the subphases. So basically by purely referring to the previous time we asked for subphases. So in fact, we recursively descend in dimension. Or length of list. Now, one thing that is important this is important to maintain what we are building to actually come out as a chain complex. We need to choose and stick with and ordering on the list of vertices in each sublex. So when I'm writing, here I'm writing just a set. There's no order, no implied ordering on the vertices. But when we start computing simplicial homology, it's important to enforce an ordering. It doesn't exactly matter what the ordering is, so long as you keep track of it. And stick with it. So, notationally, I use square brackets to call out the fact that I'm paying attention to order.
Is in a list.
Yes,
Yeah.
as in a Python list, exactly. So rather than a set, I'm saying it's a list, so I care about which one comes first in the list. Yeah.
In Python, when you see that something is iterable, does it mean that it has a natural ordering?
Yep.
Okay.
Natural linear ordering, in fact. It's got a total order. One, then the next, then the next, then the next. Yep.
Did you borrow that from Python, or did Python borrow that from math?
Oh, Python's much older. Much newer, rather. Math is much older.
Okay.
Math is much older. Although, admittedly, I've seen round brackets used often.
Okay.
And I'm explicitly making the choice, since we're using Python, to use Python syntax.
Okay. I would-
But, well, so strictly speaking, I have no idea. Okay. It's going to be folk etymology, sorry.
Are tuples iterable in Python?
Tuples are not.
I know that they're not changeable.
No, they're not iterable. Okay. At least I don't think they are. That's a good question.
Because you know,
You can do like for I and J in a
Yeah.
tuple.
In a
order,
tuple, you
order
can.
matters in a tuple.
Yeah, all right.
Because if it didn't,
Yeah, they must be iterable. You're right. I'm totally wrong there. Okay, anyway. I'm not, look, I may be a MATLAB expert, but I'm not as good on Python. Okay, right, so here's the idea. We're going to start off with these simplices, the simplicial complex. And what we're going to do is I'm going to tell you what the spaces in my chain complex are, and then I got to tell you what the maps are. And of course, the maps are more important. The spaces come along for the ride, and that's the way it is. So my agenda define my C define my boundary maps, I'll call it just. And finally, that is a chain complex. Now, these are usually called chain spaces. And these are called boundary maps. And this is usually called simplicial chain complex. Once you've gotten to this stage here, we can use the homology machinery that we've thus far defined to compute the homology of it. So basically, in terms of the process that I mentioned at the beginning of the lecture, we're going to start out with an abstract simplicial complex X, and we're going to build a chain complex. Everything that we've thus far talked about will then carry us the rest of the way to homology. Okay. So, that's the plan. First, I'm going to define the chain spaces. They're really, actually very easy. So, for an abstract simplicial complex, X, CK of X is, well, it's a vector space whose dimension is the number of K simplices of X. And in particular, I'm going to be thinking of this in particular as a vector space whose basis is the list of K simplices with their chosen ordering. Now, the ordering doesn't play a role on CK itself, but I'm remembering the ordering because it'll play an important role when I want to write down boundary maps.
Because sets are unordered.
Sets are unordered,
Yeah.
as are vector spaces.
Yeah.
So I'm going to just remember the ordering. I'm not going to use it. This is just going to be held in memory. And for all practical purposes, assume that we have real coefficients, but this is not critical. You can certainly work with integers, certainly work with other fields. If you want a vector space over a different field, that's fine. You can do this with a general ring, that's totally fine too. From a computational standpoint, since we're using NumPy, we're basically using the reals, although of course we're using the floating point reals. Pluses and minuses there, hence the tolerances and all that sort of nonsense. If anyone knows, perchance, of a good Python finite field linear algebra that is actually efficient and is based on some reasonable compiled code, I want to hear about it.
The linear algebra library?
Linear algebra library, Python module preferably, but it doesn't have to be Python per se. It does finite field linear algebra exactly. I want to know about it.
But the thing is, you want it to be free. You want it to be Python or something else that's free.
Well, I mean, I of course don't want to have to pay for it, yes, but if it's something that I have to pay not a whole lot of money, I would still be interested.
Okay.
Why, are you starting a business?
No.
Okay.
Sounds like a niche market.
It is a rather niche market, admittedly. Okay. Anyway, that's what the chain spaces are. So basically just count up the number of K simplices, call that the dimension of your space and you're good. And imagine that the basis elements, i.e. the rows, are just calling out, are named or labeled by each of those K simplices. And each of them is given a specific order that you've chosen from the outset. Okay, that was the easy part. Now I have to do the hard part of defining the actual boundary maps. Now, boundary maps suggest that I'm going from something high dimensional to something small dimensional. Finding the boundary. Find the boundary of K simplex. Well, what is the boundary of a K simplex? Well, it's a whole lot of K minus 1 and K minus 2 and K minus all the rest. Now, if I'm building a chain complex, that chain complex goes from CK to CK minus 1. So I only need to go down by 1 I could go down again, but if I do this right to chain complex, that second composition go down once and then again, that should be 0. Okay, so let's build that definition. Okay. And there are two schools of thought for how one should present what the boundary map is. School of thought number one, kind of embodied by Hatcher, is to give you a bunch of examples about what it should be, and then work up the general definition. School of thought number two, embodied actually by many physicists, judging by what I've read, this is kind of the way that I learned it, is here's the definition. It makes no sense. Now let's try to justify why it makes sense and why we should believe it. I don't know which way to do it. I'm going to write down the definition. I'm going to leave it up there a bit, draw some pictures, and sort of bounce back and forth. Okay, so boundary map. Well, so we give them this special boundary symbol just because it's historical. They're going to go from the K chain space, the chain space built at the K dimensional simplices, to the K minus 1 chain space, spanned by all the K minus 1 dimensional simplices. And it's got to be a linear map, and it's going to do something boundary-like. And let me, as advertised, let me give you the definition as a formula, and then show you in pictures what it does. So what I'm going to do is I'm going to tell you what it does on a basis element. So it's going to take as input, it's a linear combination of K-simplices. Now I don't quite know what a linear combination of K-simplices means. Or it's a basis, what is CK? It's a vector space built up of K-simplices, as in each row in that vector corresponds to a K-simplex. And then I've got some coefficients on it. I don't know what the coefficients do. But they're in there, so let's write. I equals 1 to whatever, I don't know what they are. In fact, actually, let me just even do it this way. Erase. It's a sum.
But it's a finite sum. That's important.
Well,
You're going to tell me it's not finite?
Well, there's a way to make the definition work if it's not finite. Yeah, absolutely.
Okay, but we wouldn't.
But this is a computational class, so. All right. So I'm going to walk over my finite number of simplices. Thanks, Dave. These are my coefficients. These are real numbers.
Is that, what is
It's
that?
a sigma.
Oh.
That's a sigma. And then one of these things is going to be kind of, this thing is a K simplex. So this is what the map is going to do. It's going to take something that looks like that, some kind of formal linear combination of simplices, and it's going to spit out something in terms of those simplices. Now, I want this map to be linear, because that's how my chain complex is built. So let's do that. So let me, first off, because it's linear, I know I should be able to do this. Sum over sigmas, A sigmas, and work just on one. So now, this is still in R, but this thing here, this thing has got to be some linear combination of K minus 1 simplices of X. Now, because this is going to be, because I've assumed from the outset that I've got a simplicial complex, well, if I pick simplices that are faces of sigma, so if the output of this thing is basically just simplices of sigma, then they will definitely lie in that space. Okay, so what I've done is I've sort of passed the buck a little bit. I've defined, I've said basically I want a linear map. I now need to tell you what happens on basis elements. Okay, so now let me do that. Suppose sigma is now ordered list, k simplex, there are k plus 1 vertices, v0 up to vk. Ordered list. Now, boundary k of sigma is boundary k of this ordered list. And now I need to tell you what that is. And remember I said it's a linear combination of some of the k minus 1 simplices that live in X. Now, I called this a boundary map. If I have a filled-in triangle and I want its boundary, it's going to be those edges, roughly speaking. It's going to involve some sub-simplices, some k minus 1 simplices. Notice if I delete any one of the vertices from here, I get a k minus 1 simplex. It's a sub-simplex of the one I started with. Because I've got a simplicial complex, it's definitely in X. And it feels like it's boundary-like. So, without further ado, the formula, as advertised. This is the linear combination you should choose. Notice this thing here is of length k plus 1. This thing here, even though I've used more symbols to write it, notice I went up to I minus 1, forgot I, and kept going, and I plus 1 up the rest of the way. So this is actually length k. Put another way, the I is deleted from my list. And depending on which vertex I deleted, the parity of it, even versus odd, I either counted in with a minus 1 or a plus 1. Now, this thing over here is definitely then a simplex in my complex because it is a subset of the original set. So this guy here is a subset of this simplex, so therefore, because I've got a simplicial complex, it's in my simplicial complex X, therefore it is a k minus 1 face. Therefore it is, this linear combination of those faces is in here. So that's the definition. How many people think this makes perfectly obvious sense? Good, no one is lying. Excellent. Because I have to admit, when I first saw this, I thought it was completely ridiculous. And it's still rather impressive that it works. So, theorem, which we'll prove in a little bit. This, if you use this as your definition of the boundary maps, then in fact you get a chain complex. And has to do with a little bit of combinatorics. Now, why would something like this make sense? Well, I haven't drawn my promised pictures. Now let me do that. The promised pictures really come about, really are most obvious in 1 and 2 dimensions, i.e. for boundary 1 and for boundary 2. Boundary 0 is sort of a corner case. How many negative 1 dimensional simplices do I have? How many negative 1 dimensional simplices do I have? How many lists do I have of length 0?
1.
1. And, or maybe even like 0 or something. So boundary 0 is just the 0 map. So really all the action is in boundary 1, boundary 2, and then of course all the higher ones, well, they end up not fitting on board nicely. So let me show you what happens in boundary 1. me give you an example. Actually, let me give you an example first of this simplicial complex, and then this simplicial complex. Label this one, I'll say this is 1 and 2, this is 1, 2, and 3. So the simplicial complex in particular, 1, 2, 1, 2, and 2, 3. And of course the empty set, which I've ignored. So notice I'm ordering my simplices. I've chosen an ordering. Doesn't matter what the ordering is, but I got to choose it and stick with it. So if I ask for what is boundary 1 of that simplex, well, let's use the formula. What do I have to do? Well, I'm going to first delete the 0th entry. This being Python, that's the first entry in the list. So that means I delete the 1. And I do -1 to the 0. So that's just 2. That's just coming in, that's 2. Now the next thing I delete is I delete the 2. And it comes in with a -1 to the 1. So this is what I get. Now you might say, what the heck's that? Well, it's not obvious what that is at all. Give me that.
1?
Hmm?
List that contains 1?
No. No, I can't subtract these lists. What do you mean? No, this doesn't make any sense. Right? Seriously, doesn't make any sense. It's some kind of labeling on the vertices. And that's really the best way to think about it. Really what we're doing here is I'm putting a -1 here and a +1 there. When I asked for the boundary of this edge, I ended up with +1 and a -1. And I'm going to start labeling things. Now, let me do it over here. Could do the same. This guy is still just the same as I got over there. So I don't need to redo this one, but let me do this one. Boundary 1 of 2, 3. What's that going to be? Well, delete the 2, so I've only got 3 left over, and that comes in with a plus. Now, let's sort of label this. That's according to this label. In fact, let me do it in a different color. Now, if I add these two edges, it's kind of like I've got a longer edge, isn't it? It's kind of like I've got a longer edge. Well, what does that look like? Well, let's just add them together and see what we get. Of course, we can all do the arithmetic. This is the first one. It's supposed to be minus, plus, 2, minus 1. Of course, the 2's cancel, and I'm just left with. So what I've done is I've highlighted the simplices that I was interested in, and I've come out with marking literally the boundary, the start and the finish.
So you can add the edges inside the boundary now?
Well, okay, so let's trace the formulas that I'm using over there, because everything that I'm using on this side is what I've written over there. So this formula and this formula are just cases of this one. All right. This formula, where I'm adding these two guys together, that's this. It says, I'm assuming linearity. Yeah?
So would that mean if I hypothetically had a 1, 2, 1, 3, 2, 3, and a 1, 2, 3, like the boundary would look significantly different just because...
You're stealing my next example. All right, let's do it.
Oh, sorry.
No, that's okay. That's okay. Yeah, you're trying to loop it.
Yeah.
Loop-de-loop, exactly. But let's get there. This is why the topology is important. But no, basically what happened is this two got canceled out. Now, this is something that you might have seen before in advanced calculus, Green's theorem. For Green's theorem, you're tracing around boundaries of things and seeing what's been captured inside. really, what we've got going on is this sort of thing. The ordering on the simplices, or ordering on the vertices, is tracing out an ordering. And is saying kind of started out at 1, then went to 2. Started out at 1, went to 2. Kept going, picked up at 2, and went to 3. Yeah.
So would this just continue telescoping?
Yep. Sure does. And so it continues telescoping until exactly what Chris just said. Is that if we loop around, something cool happens. All right. Operationally, we've got this formula in hand, and it's in your notes. So hopefully you guys will keep me honest with my signs.
But with partial 1, you're only summing up to 1. Oh, but then you have 0, 1 because you have.
Yep, 0, 1. I'm in Python. All right. So let's do one more example with partial 1. 1, 2, and 3. And here what I'm going to do is I'm going to choose lexicographical ordering here. So this is 1, 3. This is 1, 2. And this is 2, 3. And I'm also going to look at this one. Okay, and if I mark up the edges with these little arrows saying who goes first and who goes second, notice I've chosen different orderings on things. Okay, here we go. So let's compute.
So for the second one, the boundary just be nothing.
Yeah, hold on, we'll get there. Yeah, that's exactly right. Versus this one. And I have one more I want to compute. Because this answers an orientation question. In particular, what do we compute when we're computing homology? We compute kernels, don't we? We're asking for things that map to 0. That's what we're after. We're going to be asking for things that make boundary 1 equal to 0. Okay, so now let's actually compute this. So this first one here, it is 2 minus 1 plus 3 minus 2 plus 1 minus 3. Of course, if I've done my arithmetic right, everything can side cancels. Let's check. See, 1 cancels with 1, 2 cancels with 2, and 3 cancels with 3. Yup, to 0. Okay. Now what about this one? 2 minus 1. 3 minus 2, 3 minus 1. Okay. Well, let's see. I see a 2 cancels with a 2. And like no other canceling happens, because I end up with 2 3s and negative 2 1s. In any event, not 0. So in particular, when we start computing homology, we're going to be looking for things that have kernels. This is kernel, this not so much. But what about this one? Well, in this particular case, notice minus sign is a coefficient. But I've asked for a vector space. So that minus sign in the coefficient saves the day, and everything inside cancels. 1 minus -1, 3 minus 3. And 2 is 2. So 2 cancels, the 1 cancels, and the 3 cancels. This is actually why I said it doesn't matter what the orientation is as long as you stick with it. Because if you chose a silly orientation initially, when you start looking for the kernel, well, you just pick up an extra minus sign somewhere else. Yeah.
So 0,
Yeah.
that's just, is that an empty set? Is that nothing? Is that
No, it's a
number?
0 vector. It's a 0 vector.
vector.
It's a 0 vector. Remember, these are basis elements in a vector space. C0, which is where this thing is getting mapped into, is a vector space whose basis is given by all of the vertices. So this is an abstract basis. This is pointing in the 2 direction, whatever that is. It's pointing in the 1 direction, whatever that is, but it's certainly different from the 2 direction.
Lovely.
And this is pointing in 3 direction, which is, yeah, different and linearly independent from the 1 and 2 direction.
So V, those are different vertices?
These are different vertices. Yeah, they're lists of vertices of length 1. So they're just names of vertices.
So the negative sign down there is just basically saying you're flipping the arrow.
That's exactly right. This minus sign right here says this was a stupid choice for the arrow. Make it go the other way. Now, of course, there are other elements in the kernel of this thing. Lots of them. The kernel is a whole vector space. It's not canonical, your choice of elements of the of basis for the kernel. It's just one of them. Yeah. Go ahead, Brian. You look very, very confused.
So those maps are equal?
Which maps? That all of this stuff cancels out.
Yeah.
Why? Look, this is 2 minus 1. 2 minus 1, we just did the 2 minus 1 over there.
Yeah.
And by symmetry, this is 3 minus 2 and 1 minus 3. And then just doing algebra on this, stuff cancels out.
I thought you said that we couldn't add up the list things.
Oh, I'm not, though. These are vectors. So if you like, you could set up the following correspondence. You could make a vector like this and say this is what I mean by 1. And in fact, this is what we do in software. This is what I mean by 2, and this is what I mean by 3. Now I've got a correspondence between the linear algebra basis and this abstract basis. Yeah.
So just hypothetically, if I had a 1, 2, 3 orientation at the top right triangle, but I also had the simplex 1, 2, 3, so it was a filled-in triangle,
Yeah.
the boundary of 1 ignores that inside consideration, right?
Yes, that's the point.
Okay.
That's the point. Yeah, we haven't gotten there yet, but yes, that's the point. In fact, that's
Whereas like boundary 2 would ignore all the edges.
yeah.
And,
So in fact, that's exactly the next example I want to put on the board when everyone's happy with this.
okay.
Why could you switch the sign in that bottom?
Here?
Yeah.
Well, because again, this is a basis element. This is for C0
Yeah.
of x. Now, C1 of x has a different basis. The base is spanned by 1, 2, 2, 3, and 1, 3. Now that basis doesn't specify the vector itself, the coefficients in that basis do. So here I've chosen a 1 coefficient, a 1 coefficient, and a -1 coefficient. Perfectly within my rights, once I've got a vector space, to put -1 as one of the coefficients. Here I've chosen a 1, and a 1 for the 3 coefficients. This is also a 3-dimensional vector space. Dimension 1, 2, 3, for instance. Just as what I've got going on here. Dimension 1, 2, and 3.
So if we're applying this to real data, where would we get, so we would have to get, from theory, we would have to be able to come up with our 1, 2, 3 diagram?
Your simplicial complex. Yes.
That has to come from the theoretical.
That is the thing which, once you give me that, then we can analyze it.
Okay, but once we have it, we're good.
Once you've got the simplicial complex, you are good to go. Without that, that becomes somewhat more of an art. As my friend Cliff likes to say, that's modeling, which is a perfectly legitimate discipline, but that's not math, it's modeling. Okay, so now let's take the example that Chris just suggested, and let's throw on a 2 simplex and take a look at its boundary. Are you done copying?
No, I should take a picture.
Okay. You got this?
Yes. These are problems they couldn't solve.
Yeah, well,
Oh, that's true.
but hopefully we actually get visibility on the screen, unlike the previous ones. Not so good. All right. So now our 2 simplex example. Well, it's really the same thing, but it does take some poking around to see what it's doing. Okay. So, same. But now I'm going to fill in the interior of this thing. And I need to pick an ordering on these. Why did I say the ordering is 1, then 2, and then 3? So let's ask, what is boundary 2 of 1, then 2, then 3? Being careful to pay attention to the ordering. Okay, well, it's this sum, alternating pluses and minuses by deleting the vertices. So off we go. The first orientation, the first sign is a -1 to the 0, so that's plus. And it's delete the first guy in the list, the 0th guy in the list. Then the second one is a minus, delete the second one in my list, i.e. index number 1. And then in with a plus. Now, let's see what this looks like in terms of orientations on the one-dimensional surfaces. 2, then 3. 1, then 3, oh, but with a minus sign. 1, then 3, but with a minus sign.
Is it going from 3 to 1?
It's going to do 3, then 1. And then 1, then 2. So look what it's done, is it's enforced this, which we just computed what this did. Of course, this is then, in fact, the same thing we just found out. My point being, you can switch the orientations around so long as you're consistent. Keep your minus signs floating around in the right way. Beware of the minus signs. Take my warning seriously. As someone who has been messed up by minus signs at the board. Hopefully not today. Okay, so now, remember we said this thing's got to be a chain complex, right? We just did this one on the previous board, and we found out that boundary 1 of this kind of thing is 0, right? So boundary 1 of that junk so in particular, boundary 1 after boundary 2, 1, 2, 3.
If you switch the arrow, do you have to switch the
Sign.
order?
You have to, if you switch the arrow, you switch either the order or the sign.
Either.
Either.
How come you switch both? One for
Oh.
minus.
No, okay. You said if you switch the arrow, I'm keeping the arrow the same.
So you switch both.
Yeah,
Okay.
I wanted to keep the arrow the same. If you want to switch the arrow, actually, then you pick one or the other. I wanted to keep this the same, but I wanted the sign. Go on.
Okay. Is the arrow the same thing as the order?
Yeah. Yeah, it's capturing the same thing. They're all different representations. If you will, this is sort of the most basic, mathematically precise representation. These pictures here kind of crap out of this dimension. They don't work much better. But here, I mean, I could have, you know, a list of length 15. Take me a while to work through all the simplices, but you can do it. Now, here's the thing. The thing is, this composition, if that works in general for every simplex, certainly worked for a 2-simplex. It's the first case of a 2-simplex. This works for boundary k minus 1, composed in the other order against boundary k minus 1 of boundary k of every k simplex. If that comes out to be 0, then we're done. We've got a chain complex. The proof of that is actually really not hard to show, and I can even show you that in the last 3 minutes class. I don't see a frown, though.
No, I just tried rearranging order, it didn't make a difference. Double boundary 2. We just did 1 through 2.
No.
And you still get 0.
Well,
After you
okay,
call
so look, if I left the sign alone, then I would have gotten a 3, 2 3s and a minus 2 1s.
No, I mean, so for example, say I did boundary 2 of 1 through 2.
Boundary 2, oh yeah.
It doesn't make.
No, it doesn't make a difference. It doesn't make a difference at all. Actually, you'll see that theorem. Boundary k minus 1 of boundary k of and the proof of this, as I said, I can do in the last few minutes of class. Well, how does this work? Boundary k minus 1 of, let me just write out the formula. I equals 0 to k of minus 1 to the k, v0 up to, rather than writing up to minus 1 and then plus 1, let me save and put a little hat to say I'm going to get rid of it. This is standard notation in the field. Just a little hat says ditch it. Okay? Now, what's this going to be? Well, it's going to be basically the same thing, except now I'm going to be doing it via linearity. This is a k minus 1 simplex, so that's legit from a type standpoint. It's also going to be the same kind of structure. Oops, this is not k. This is I. This is now going to be another sum. It's going to be a sum, j equals 0 up to k, but j is not allowed to be I because I've already deleted that one. And now you need to be a little bit careful about the minus signs, though. See, the minus signs up to I are just as you'd expect them to be. They're just minus 1 to the j. But afterwards, they pick up an extra minus sign. Well, that's sort of awkward. So rather than writing it out like this, let me write it like this. You go up to I minus 1. In that case, it's just negative 1 to the j. v0 up to, and I'm going to ditch vj and vi. But now, in addition, I'm going to add the rest of it. I plus 1 up to k. And now here, I pick up an extra minus sign because I'm skipping over this. I would, if I'm going in this original list, it would be delete the vj one, but this one's already gone, so I've shifted over by 1. So this is now j plus 1. And notice vi and vj are now in opposite orders. Same set of simplices, but I just deleted them in opposite orders. Well, deleting in opposite orders doesn't matter. But if I say pick this simplex where I and j are where I is equal to j in the I here, or rather, the I here is the j here, and the j here is the I here. You get what I'm saying? I've got a list, and I've deleted these two entries. I could delete this one first, then this one, or I could delete them in the opposite order. This one here, I've deleted the second one first, and then the one before. This one here, I've deleted the first one and then the second one, in that order. And notice they come in with exactly opposite signs. Because they've come in with exactly opposite signs, they cancel out, and I'm done. And
Why is it that they've come in with exactly opposite
okay.
sides?
Because think about what's happened. What's happened is I am walking down my list, and normally, if I had this list up from V0 up to VI, that's just what I would expect. But now if I take one step further, VI is not there. According to my formula, I don't care what the names of these things are. But everything from VI plus 1 on has shifted over 1 to the right. And so I picked up that minus sign with respect to what I would have had if it wasn't gone. You could express that as saying that this is a j plus 1, and then everything cancels. And that is it. End of proof. Yeah.
Is that just explaining, maybe like, how, the way of getting like the 2, 3, and the 1?
Yep, that's exactly what it is. That's exactly what it is. This is a brilliantly clever trick. It's one, whenever you want a chain complex and you don't know how to get it, this is how. This kind of stunt makes it come into existence. It's also been said by some very smart mathematicians, orientation of which this is actually, although computationally a very simple concept, it's conceptually a very difficult concept. Because it's understanding how to pack this sign cancellation into things that are not just ordered lists of names. And that's not remotely obvious. So with that, call it, end, and next time. Bye.
How are you going to do inductive proof?